All right, so let's get started. We got a new chapter that we're going to start in on, chapter 19. And this is on the study of thermodynamics. So we're going to be building off of what you guys learned about thermodynamics last semester. Okay? Anytime we say thermodynamics, we're talking about the study of energy in a chemical reaction or a phase change or some sort of a chemical process. All right, so thermodynamics is always focused on energy. And energy is something that's a little weird because it tends to manifest itself in different ways. All right, so we're going to talk about a few different forms of energy here today. Okay, so first of all, a good place to start is with the laws of thermodynamics. The first law of thermodynamics is one that you're familiar with already. Just call that the conservation of energy. All right, so this first law of thermodynamics states that energy cannot be created or destroyed only transferred. All right, so the universe, it's got a set amount of energy in it. We're not making any more. We're not losing any. All right, all we're doing is transferring it from one form to another. So just a very simple example would be your car that runs on gasoline. How does that do it? It doesn't create any new energy to get going. It doesn't destroy energy. All it does is transfer the energy from the chemical bonds in those gasoline molecules into work, into propulsion down the road, right? So it's transferring energy from one form to another. Energy that was in chemical bonds is transferred into kinetic energy, into motion. All right? And what we're going to do now is introduce the second law of thermodynamics. We're actually going to kind of build up to this. So to start out for our second law here, we're just going to start with some observations that scientists had made at this point, and then we're kind of going to build off of them, formalize them here. All right? So one thing that scientists had noticed is that the universe hates concentrated energy. They noticed that all these chemical processes that they were observing, they were spreading energy out, all right? And that is very much so something that's true about our universe. It does not like concentrated pockets of energy. It's constantly trying to spread everything out. So there's going to be a point in time where we're long going to be gone, but where our entire universe is going to kind of run its course. Every bit of energy that's densely packed into stars and things like that will all be evenly spread out across all corners of the universe. All right, that's what the universe is sitting here trying to do. Get rid of us. Spread out all this energy into all the corners of the universe. Okay? And so then the other thing that we're going to note about our universe here is we're going to think about it as the ultimate tax man. Nothing's allowed to occur in this universe without the universe getting a cut of the energy that's produced, what we call a heat tax. All right, so again, our topic here is thermodynamics. We're studying energy in chemical reactions, and in particular, we're going to focus on whether or not a reaction can actually occur. We can dream up a whole bunch of different reactions, doesn't mean that it actually occurs, right? So what are the rules here? What chemical reactions are actually allowed to occur? Okay? And if what we sort of have to tune our thinking about is it's really the universe that's either letting these things happen or not. It's not like we get to decide we want this reaction to occur. There's something more fundamental going on here where certain reactions are allowed and certain reactions are not allowed. Okay? And so what these scientists did, and this was crazy long ago, like 1870s, 40 years before we even had proof that atoms existed, they came up with this theory. No idea how. Smart people. All right, anyways. Their goal, what they set out to do, is they wanted to find what's called a chemical potential. All right, so this is our goal for this lecture here. We're trying to find what we're going to call a chemical potential. All right, and the goal here is this chemical potential is to find a value that allows us to determine, that tells us whether a chemical process, a reaction, or a phase change will occur. All right, so again, what are the rules here? Can we find this number, this value that we're going to call a chemical potential? And if we know the value for this reaction, we can determine whether or not these reactions occur. Okay? So, a good starting place here for our chemical potential is that one factor is going to be this thermodynamic quantity that you discussed last semester, delta H, which is what's called enthalpy. All right, they know that this enthalpy value is going to be important for our chemical potential. It's going to be an important factor there. They've been studying enthalpy for a while. This is something that's fairly easy to measure. You guys did this in the lab last semester. If you perform a reaction, you can simply measure the increase or decrease in temperature that occurs, and from that calculate this enthalpy value, right? Thermometers. Pretty old school instrument. They had those back in the 1800s, right? So they could get these enthalpy values, these enthalpy measurements pretty easily. And having studied a bunch of chemical reactions, they know that a lot of these reactions that occur spontaneously have releases of energy, negative enthalpy values. So they know that this is going to be an important part of their chemical potential, but it can't be the whole story. There's something else in this equation that's missing, all right? And that's what we got to figure out, okay? Let's start by rewinding and reviewing enthalpy here. Again, something that we discussed last semester, but always good to review. I know everybody did nothing but study enthalpy all summer long, but nonetheless. Okay, so delta H is this symbol that we use for, again, the quantity we call enthalpy, okay? And when you're measuring enthalpy, you're measuring the exchange of thermal energy in a chemical process. Thermal energy we more commonly refer to as simply heat. Okay, and heat and temperature are not the same exact thing. They're measured in different values. Heat is an energy. Temperature is measured in degrees Celsius or Kelvin or something like that. But heat can change temperature, right? So if you add heat to something, you're going to increase its temperature. If you take heat away for something, you're going to decrease its temperature. Okay, so they're closely related, not the exact same thing though. All right, and we got some fancy terminology. When delta H is a negative value, is less than 0, this is what we call an exothermic reaction. All right, this exothermic reaction, a negative delta H, this is a reaction that releases heat. Releases that thermal energy. When delta H is positive, we have a special name for that. Those are endothermic reactions. All right, these are reactions that actually absorb heat. So they'll end up absorbing energy from the surroundings as this reaction occurs. Okay? And again, our goal is to get this chemical potential. They knew that this enthalpy is going to have to be an important part of that chemical potential because they made one very simple observation when they were taking these measurements. And that is the vast majority, most reactions that occur spontaneously release heat, i.e. are exothermic. Right, so these early thermodynamics scientists, they've been dedicating to studying these transfer of heat in reactions, and they just make this simple observation that most of these reactions that are occurring in the lab are doing so in an exothermic reaction, right? They're releasing heat. But of course, there's this little caveat there. Not all, but most, right? So let's take a look at a very simple reaction that is not an exothermic reaction. Okay. If we take solid water, otherwise known as ice, if that melts into a liquid, right, we would call this melting. Okay? When water when water goes from being a solid to being a liquid, it's got to absorb heat in order to do that phase transition, right? So these solid water molecules need to absorb heat in order to become liquid water molecules. Absorbing heat, remember, is an endothermic reaction. All right, so again, they've been studying all these reactions, and most reactions that occur spontaneously release heat. And that kind of checks out, because remember, they also have this observation that the universe hates concentrated energy. It's trying to spread this energy out. So yeah, reactions that release heat, that spread that energy out, that makes sense. Those are favorable. But then they got this really obvious, glaring example of a reaction that occurs spontaneously. I think we've all seen ice melt. Right? We know it does indeed occur. The universe allows it. And yet that's an endothermic process. So why is all of a sudden this particular well-known example allowed to happen? Why is the universe allowing a reaction that actually absorbs energy? Okay? So the key here is that when you have a solid, right? Those water molecules are all arranged in this very orderly fashion. They're all fixed in place within that structure, right? So this would be a highly ordered compound. All those water molecules are in a very specific place. All right, well, when you take that solid and it melts, all of a sudden those liquid water molecules are free to move around. They can start tumbling around, flipping around in space, migrating from one end of the beaker to the other end of the beaker, right? It's kind of like they're free from that little lattice. And so what you've created is a more disordered state. So the key to why the universe is allowing this process that is absorbing thermal energy to occur is because it's transferring something that used to be very highly ordered into something that's very disordered. Okay? This is what's known as entropy. All right, we talked a little bit about entropy before, and it's the weirdest thing in the world. It's this universal push towards a more disordered state. All right, so again, our observation here, the universe wants to spread out this energy. It hates concentrated energy. Well, one of the ways that it does that is through the release of heat in an exothermic reaction. Okay? But if a reaction actually absorbs heat, it can still be allowed to happen if it spreads out energy by creating a more disordered state. All right? So we have another component to our thermodynamics here that we're going to introduce. Again, this is what's called entropy. We use this delta S symbol for entropy. All right, so our definition for entropy here, we're going to kind of have two. One's going to be the helpful way to think about it, and then we'll have the more formal definition as well. All right, so entropy is this energetic push towards a more disordered state. Which I know sounds really weird and something that you just kind of got to wrap your head around, but the universe is constantly pushing us towards a more disordered state. Okay? It's bizarre, but for every chemical reaction, you can literally go in and measure an energetic contribution to just how much disorder that reaction creates. Okay? And again, we call that entropy. The sort of strictly speaking statistical mechanics definition here is entropy is the number of chemically equivalent ways to arrange a system. All right, and this is the very wonky kind of statistical mechanics definition here. Truthfully, I just think about it as an energy of disorder. That's the more helpful one. All right, but this, again, the statistical mechanics, if we look at our simple example up here of a process that is, entropically favorable, we start out with these highly ordered water molecules. There's just fewer ways for you to go in there and arrange these H2O molecules in order to create that solid structure. Everything's got to be in a very particular place. Everything's got to have a particular orientation to it when you put it in this structure, right? We have this liquid water is more entropically favorable because there's just more ways for you to organize those water molecules and create that same system, okay? Anyways, think about it as an energy of disorder. It's more helpful. All right, so what we're going to do is we're going to look at a few processes and try to determine whether they are entropically favorable or unfavorable. All right, so when delta S is positive, that would be an entropically favorable process, right? Positive entropy is good. When delta S is less than 0, that's what we call an entropically unfavorable process. All right, so let's look at a few examples and see if we can't determine whether they are entropically favorable or unfavorable. All right, so what about the freezing of H2O. Going from the liquid state to the solid state. All right, and what we want to ask ourselves is this process creating more order or disorder? If I take liquid water molecules and they freeze into this solid form here, have I created a more ordered state or a more disordered state? More ordered, and the universe hates order. All right, so this would be an example of an entropically unfavorable process. So let's take that same liquid water, but now we're going to boil it. It's going to go from the liquid phase to the gas phase. All right, would a gas phase be more ordered or disordered? More disordered. So this would be an example of an entropically favorable process. All right, so I'm going to leave some room for some more examples here, but I'm going to make some notes at the bottom here, because what we're really sort of comparing are these states of matter. A solid is more highly ordered than a liquid, which is more highly ordered than a gas. So those states of matter are really important for sort of qualitatively determining the entropy of a reaction. All right, so we're just going to make a list of entropically favorable processes. All right. And a huge factor, we're going to put it number one at the list here, is that solids are more entropically favorable than liquids. Gases are more entropically favorable than liquids, which are more entropically favorable than solids. All right, that's a huge contribution. There is a huge difference in the amount of disorder that you would have in a canister of gas versus a canister of liquid, right? So there's a big jump in entropy that you would see for these phase changes. All right, let's take a look at another example. We got tetranitrogen dioxide gas decomposing into two dinitrogen monoxide gas molecules. All right, so if we think about this here, we are going from one gas molecule to two gas molecules. Which one is going to be a more disordered state, having more or fewer molecules in there? More. So this would be entropically favorable. All right, so another important factor here is just more particles is inherently more disordered. All right, what about if I dissolve sodium chloride? I take solid sodium chloride and I mix it with water so that I have sodium ions and chloride ions. All right, is dissolving that solid to create this aqueous solution, is that creating more order or more disorder? Disorder. So this is also entropically favorable. All right, so creating a solution. Although we're going to put a little asterisk next to this one because it turns out it's a little more subtly complicated than we're going to treat it right now. All right, so what if we just decrease the temperature? Like we have carbon dioxide gas at 100 degrees Celsius, and we just let it cool down. We still have carbon dioxide gas, but now it's at 10 degrees Celsius. Okay, which one do we think is going to be a more disordered state? Higher temperature or lower temperature? Higher temperature. So remember, all temperature is doing from the standpoint of a molecule is increasing its kinetic energy. Things are just moving around faster, right? So at a higher temperature, there's much more disorder, much more chaotic movements going on than you have at lower temperatures. So this would be an example of an entropically unfavorable process. All right, so these last two are sort of lower on our list of contributions here, but anything that increases temperature will increase entropy. All right, and another pretty minor contribution, but nonetheless we want to note, is if you were to increase the volume. All right, so if my canister of CO2 is 1 liter, and all of a sudden I increase that to a 5-liter canister, those carbon dioxide molecules just have more positions that they can occupy. Okay, so that would also be a contribution to the energy. Right, and so to be clear, this little list that we made is kind of in order of importance here. All right, again, state of matter being the big one. All right, so these big brain scientists back in the 1800s, they stumbled upon this enthalpy thing. They studied it for a while. Couldn't be the whole story. They realized that there's this entropy contribution as well. So now we can go back and formalize our second law of thermodynamics here. All right, so the second law of thermodynamics is that all spontaneous chemical processes increase the entropy of the universe. All right, and in science, we have theories, not laws, but these things have gotten a special name because they were proposed way back in the day, and to this day, nobody has been able to find a crack in them, right? They have stood the test of time over and over and over again, which is why these are not just the theories of thermodynamics, but the laws of thermodynamics, okay? So it turns out that every chemical process that's allowed to happen spontaneously is only allowed to do so because it increases the entropy of the universe. All right, so we can make this same statement here by just saying that the delta S of the universe has to be greater than 0. All right, if it's going to happen, it has to increase the entropy of the universe. That's the rule. All right, so the universe is pretty big. Okay, so what scientists feel like it's very helpful to do when they're designing a chemical reaction is they're going to cut that universe up into two parts. There's going to be the system. Okay, the system is what you're studying. All right, so if you're doing a chemical reaction, for example, that chemical reaction in that beaker, that would be your system. All right, everything else you would lump into what you would call the surroundings. Okay, so the universe, we're going to cut it up into two things. That beaker that we're studying our reaction in, and then everything else. That's the surroundings. Okay? All right, let's just take an example reaction here. This would have been one of the first types of reactions y'all studied last semester. If you take sodium chloride, you can mix it with silver nitrate. All right, two aqueous solutions. You'll get aqueous sodium nitrate. All right, but then you will get a precipitate, solid silver chloride. All right, this is one of the reactions that you would have done in the lab last semester. You mix these two clear, colorless solutions together, and you get this like nasty, milky white substance, right? And that white particulate matter floating around is your solid silver chloride that you've created through this precipitation reaction. Okay, so everybody take a look at this chemical equation real quick and tell me whether this is entropically favorable or unfavorable. We have a solution that we're mixing with another solution to create a third solution. But then this highly ordered solid here, so would this be entropically favorable or unfavorable? So this would be entropically unfavorable. All right, so this is an entropically unfavorable process, but we did it in the lab, right? Y'all saw it in front of your eyes. This does indeed occur spontaneously. So this is still a reaction that does occur. So how does that work? We just said that in order for something to occur, it has to increase the entropy of the universe here. All right, well, again, we're going to break this into these two components. Our delta S for our system, but also the surroundings. Our system would be that precipitation reaction, that beaker full of those liquids that we just mixed together, right? So if this is an entropically unfavorable process, right, so we can just ask, how are entropically unfavorable processes allowed to occur? Right? how is this number allowed to be negative? Well, we got this second part over here. As long as this is a larger positive number, then that process would still be allowed, right? So this is an example. We saw this entropically unfavorable reaction happen in front of our eyes. So how is that possible? Well, we must have had a large contribution to our delta S of our surroundings here. Oops. All right, so as long as the delta S of our surroundings is greater than that delta S of our system, or the positive of that value, then our process would still be allowed to occur. All right, and so the key here for this entropically unfavorable reaction is that it is also exothermic. All right, so yes, that entropy contribution is negative, but it's got that release of thermal energy because it's an exothermic process. So it turns out that this delta S of our surroundings is proportional to that delta H value. It's equal to the delta H of your system divided by T. Okay, so an exothermic what this equation is basically saying, if we were going to put it into regular speak here, is that an exothermic process, something that releases heat, increases the entropy of the surroundings. So that release of heat, that heat then dissipates out into the rest of the world, and it heats up all the other particles out there, increasing their energy, right? So even though the system itself, that chemical reaction was entropically unfavorable, there's enough release of heat that occurs so that the net result is that the universe gets its increase in entropy. And that's the standard here. We got to increase the entropy of the universe. Okay, so we're going to roll this all together here. We're going to take this and plug it back in over here. All right, that way we have our whole equation defined in terms of our system here. All right, so the delta S of the universe equals the delta S of the system minus the delta H of the system divided by temperature. All right, and all we're going to do is we're going to rearrange this equation by taking the whole thing and multiplying it by negative T. Pull it out of the denominator of that delta H term. So we got negative T delta S of the universe equals the delta H of our system minus T delta S of our system. All right, and they knew that they were onto something here because this quantity does have units of energy. And so we have now arrived at what was our goal from the beginning here, what we're going to call our chemical potential. All All right, they gave this thing a fancy symbol too. This is going to be delta G. Delta G is equal to delta H minus T delta S. All right, so this is our chemical potential. This is our value here, our energy, that if we can measure it for every reaction, we can determine whether or not that reaction will occur spontaneously. All right, and again, we knew it had this enthalpy component here. What was missing and what they had to sort of add on was that entropy component there. All right, both of these contribute to increasing the energy of the universe. So they both are factors in our whether or not the reaction occurs chemical potential. Okay? If we remember, our delta S of our universe had to be greater than 0, right? That's a process will occur if delta S of the universe is greater than 0. Well, that means that if we look at our equation here, delta G would be less than 0, right? Because we have that negative T times our delta S. Okay, if delta G is negative, we would call that a spontaneous process. Something that will actually occur. You mix these two things together. Does a reaction occur? If delta G is negative, yes. Yes, it does. If delta G is greater than 0, we would call that a non-spontaneous reaction, which is kind of a fancy way of saying you mix these two things together and nothing happened. All right, so this is kind of this fundamental equation for thermodynamics that we're going to be introducing in this chapter here. Delta G equals delta H minus T delta S. And again, by looking at the value of delta G, we can determine whether or not a reaction will occur spontaneously. This is, everything now is defined in terms of our system. We get lazy and we stop writing system. But yes, it's our delta S of our system. Okay, and so again, we call delta H enthalpy. We call delta S entropy. All right, the dude who kind of established delta G, Johannes Gibbs or something like that. Gibbs was his name. He named it after himself. So this is what we call the Gibbs free energy. Sometimes just referred to as free energy. And so we can see that there's these two components for whether or not a reaction occurs, the enthalpy component and the entropy component. All right, so we're going to look at this equation here and sort of place some what if with values. Like, what if the sign of delta H is negative and delta S is positive kind of deal. All right, so we're going to make a little table here. Here's our equation. Delta G, delta H, delta S. Okay. All right, and so let me show you how we're going to fill this in here. First, we're going to say, all right, what if a reaction is exothermic If it's exothermic, what is the sign of that delta H value? What did we say that it meant to be exothermic? Have a delta H less than 0. Okay, so that'd be a negative value for delta H. And what about if a reaction is entropically favorable? Right? What did it mean to be entropically favorable? Okay, that meant that your delta S value was greater than 0, so a positive delta S. So let's look at our equation here. If we were to plug in a negative value for delta H and a positive value for delta S, what would be the sign of delta G here? Well, remember, I'm going to multiply that positive value by negative T, negative T, so it's going to turn it negative. So my delta G value here would have to be negative. Right? From the universe's standpoint, this is best case scenario. It's getting a release of energy spread out in the form of thermal energy that's being released, but also a more disordered state has been created. So it's also entropically favorable. So this is going to be a reaction that is always spontaneous. The universe is like, yes, absolutely, lots of that. All right, so then what if the pendulum swings the exact other way here and we have an endothermic reaction that is entropically unfavorable? Bless you. An endothermic process would be one where that delta H value is positive. All right, and entropically unfavorable means that that delta S value is negative. All right, if we go back to our equation here, delta H is positive minus T times a negative number, which is going to make this positive. So what's delta G always going to be? Positive. All right, meaning that the universe says absolutely not. Both an endothermic process that is entropically unfavorable will never be allowed to happen. Non-spontaneous. All right. So now what if it's exothermic, but entropically unfavorable? All right, so this is a reaction that releases heat, but ends up creating more order. So it has a negative entropy value. All right, if we look at our equation here, this is a negative. Minus T, negative. All right, so that negative T times that negative value makes it positive. So is delta G going to be positive or negative? It's going to depend on that temperature. Let's go all the way to the low extreme here, 0 degrees Kelvin. Would this reaction be spontaneous or non-spontaneous? If I plug in a 0 for T here, is it going to be negative or positive? This contribution is gone altogether, so my delta G would be negative. Okay, so at really low temperatures, this reaction would be allowed to occur. But at really large temperatures, as this contribution gets bigger and bigger and bigger, all of a sudden that would be a positive delta G, right? So again, it's going to depend on temperature. We're going to see that at low temperatures, this would be spontaneous, have a negative delta G. All right, but then you're going to get to some high temperature, and it's no longer allowed to occur. All right, so we got this push-pull between these two terms here, our enthalpy and our entropy term. They're kind of in conflict here. From the universe's standpoint, it's exothermic, which is good, but it's entropically unfavorable when it's bad. And as you can see from our equation here, the contribution of that energy term is dependent on the temperature, right? That term becomes bigger and bigger and bigger the higher that temperature is. So in this case here, this would be spontaneous at low temperatures, but non-spontaneous at high temperatures. All right, an example of a reaction that would be exothermic but entropically unfavorable, that would occur at low temperatures but not high temperatures, would be freezing. Going from a liquid to a solid, for water, for example. We're creating more order. It's entropically unfavorable. But in order to freeze, those liquid molecules have to release that thermal energy. So it's an exothermic process. And indeed, we know that this is something that will occur spontaneously at low temperatures, like in your freezer. But it doesn't occur like out here at high temperatures. I'm not worried about this all of a sudden turning into ice, right? So at low temperatures, this would be a spontaneous process. At high temperatures, non-spontaneous. Not going to happen. All right, so then the last one here would be if we have an endothermic process. So it's got a positive delta H value, but it is entropically favorable. So that entropy contribution is positive. So delta H is positive, but delta S is also positive, right? So that negative delta T, or negative T component here, all that together, that term's negative. All right, so again, let's go to the extreme here. Really low temperatures, we put in 0 for that value of T. Is this spontaneous or non-spontaneous? At T equals 0, this drops out, and I get a positive delta G value. So that would be non-spontaneous. So low temperatures, positive delta G value, so it's non-spontaneous. All right, but as the temperature goes up and up and up, and this negative term here gets bigger and bigger and bigger, eventually there will be a temperature reached, a higher temperature, where this reaction is spontaneous. All right, so once you get to a high enough temperature, that entropy component takes over, and delta G is negative. All right, and another simple example of this type of process here would be boiling. Going from liquid water to gaseous water. those water molecules have to absorb thermal energy to go to that gas phase. But this is an entropically favorable process. We're creating a more disordered state. So we can boil water spontaneously at high temperatures. We're not worried about all of a sudden water starting to boil at low temperatures.